incredible scientific adventure of an unlikely collection of scientists and engineers, dreamers and schemers who attempted the impossible: to control gravity. Gravity is the fundamental force that holds us to the Earth and binds the universe together, yet we still don't fully understand it.
Gravity is the most mysterious of all the fundamental forces.
The ultimate challenge I can think of as a scientist is to control gravity.
The scientific quest triggered a race between rival corporations, governments, and military.
It can destroy the missiles or remove them from their trajectory.
Fueled by the paranoid fear of missing the greatest technological advance in history.
If just one idea works even only partly, you won the jackpot.
If the dream of gravity control ever came true, it would revolutionize the world and could send us to the stars. In the late 1980s, aerospace engineer Ron Evans was working in the defense industry in Lancashire, England. He'd been trying to find a way to detect stealth bombers using fluctuations in gravity. And he wondered if he could take it even further. Could he use gravity to levitate a plane? Of course, it was impossible, but Ron did something a bit reckless. He asked his employer if they'd let him try. Ron's employer was the biggest defense and aerospace contractor in Europe, BAE Systems. And instead of telling him to have a cup of tea and a nap, they listened.
I had to go to the head of the technology board, it's a panel, and persuade them that it was worth doing. Now, clearly it was very speculative. I had to go away and come up with some concepts and come up with some ideas that could actually feature an anti-gravity or a gravity-type propulsion system. Well, this was one of the designs that we came up with. For a start, it wouldn't be limited to just flying in the air. It could fly anywhere, into space, even into water. Of course, it was a vertical takeoff design because it had a gravity engine inside, but it didn't look very exciting. And so we asked the artist to put some green rays underneath. That made it look far more futuristic. Let's be clear that not everyone in the company thought we should be doing it. There were quite a few that felt we make aircraft, we're good at it, and that's what we should be doing. But there were a few, and some very senior people, that felt, okay, let's just have a little look at the future. And the concept became known as Green Glow.
As head of Project Green Glow, Ron's job was to find and develop advanced propulsion systems to overcome gravity.
The potential was enormous if it happened. It would totally change aerospace.
And Ron was not alone. At around the same time in the U.S., NASA began a parallel project headed by aerospace engineer Mark Millis.
It was around 1996 when I was asked to lead the Breakthrough Propulsion Physics project. Things like non-rocket space drives, interstellar propulsion,
and manipulating gravity.
Things like that. For that project, the idea was to think radical, think big.
Today, NASA says it has moved on and doesn't want to look back.
I can't go in there to talk about it now because NASA's not doing that work right now.
At BAE Systems, the same situation. The company no longer wants to discuss Project Green Glow.
We asked them whether we could go there and talk to them about it, and they just said no.
Gravity control is a dark and dangerous science. But, like modern-day alchemy, it promises a glittering prize, but it can destroy your reputation. Years earlier, Ron had watched a gravity experiment bring down one of Britain's best-known scientists.
This time I call for a volunteer.
Professor of Engineering at Imperial College London, Eric Laithwaite.
And then we're going to spin up the biggest gyro of the day, which is here.
Like millions of others, Ron had been spellbound by Laithwaite's Christmas lecture at the Royal Institution in 1974.
I can make him raise it. Now,
Laithwaite suggested that by spinning a heavy wheel, he could make it counteract gravity. Ron has returned to the Royal Institution to try and recreate the effect.
Does it feel light?
It does. It feels very light.
With the help of fellow engineer Dr. Adam Wojcik.
If I slow down, it feels...
What I think was at the back of Laithwaite's mind was that there was a force in one direction more than in the other, and so the gyro will start to rise up. And that gives you the illusion as though it's losing weight. It isn't. It's just an illusion. But is it lighter?
When the gyroscope is rotated in the same direction it's spinning, it's given an upward lift.
If I rotate in the opposite sense...
That does look heavy. Oh, careful, careful, careful.
When it's rotated in the opposite direction, the opposite happens, and it seems to get heavier. Still hoping to make gravity control a subject of serious research, Laithwaite acknowledged his mistake. Yet his reputation was permanently damaged. He was snubbed by the academic establishment and felt compelled to leave his position at the Royal Institution.
Professor Laithwaite got into a lot of trouble with this, really because of the claim that it got lighter, which is anti-gravity. And academics jump on any anti-gravity device as being impossible. Well, it's not impossible. It's just we don't know how to do it. But we should look. It's like flight in the last century. In those days, anybody that said they could fly was looked upon as a lunatic.
The difference is that before humans could fly, we knew birds could. We could study aerodynamics. But there was nothing we knew of that could actually overcome gravity. The dream of lifting effortlessly from the Earth is not confined to engineers. Despite being so contentious, many academics are rather seduced by the idea. Dr. Tamara Davis is among them.
From a little kid, I always wanted to go and visit other planets and go up into space. And to be able to have a form of propulsion that could get me there easily would be fantastic. But we don't yet know whether we can manipulate gravity or have any control over it.
There is one fundamental force we know we can control, which we've used to build our modern world: electromagnetism. It gives us a tantalizing illusion of gravity control when we levitate a magnet. Electromagnetic repulsion balances the weight of the magnet by using the same magnetic polarity in the base.
We know that like charges repel. So here we just have a magnetic field that's levitating a magnet. So this is nothing mysterious. This is just electromagnetism. See if I can get this across.
The power of control we get from electromagnetism lies in the fact that we can change its polarity and make it either repel or attract.
So in electromagnetism, we have positive charges and negative charges, and they tend to attract each other. If you have a positive charge and a positive charge, it will repel from each other. But wouldn't it be great if we could get gravity to work in reverse and be able to levitate things using gravity? Only problem is there isn't any negative gravity, there isn't any anti-gravity that pushes. Gravity always pulls, as far as we know.
The reason seems to be that unlike electromagnetism, gravity has only one kind of polarity: positive. One mass is simply attracted to another.
Gravity and electromagnetism are completely different forces. There's a very special property of gravity. That is that it adds up.
Inside an atom, there's a positive nucleus surrounded by negative electrons. So the electromagnetic value cancels out, whereas there's nothing to cancel out its mass.
So the force on one atom adds to the force on another atom, and so they generate an attractive gravitational force. So if you get enough of those atoms together, like in a planet or in a star, then the gravitational force is very strong. So gravity is different. It adds up as you increase the amount of matter in a way the other forces don't.
In 1996, a Russian scientist working in Finland claimed to have done the very thing the skeptics said was impossible: control gravity. Dr. Eugene Podkletnov had been using a machine called a cryostostat to cool electrical superconductors when something very strange happened.
One evening, we were working with our cryostat, and one of my colleagues, who was living at that time, just came to the laboratory and said, "Guys, what are you doing here?" And we said, "Just working." And he was smoking his pipe. A very interesting person. It is, by the way, not allowed to smoke a pipe at the laboratory, but it was late in the evening. And he blew his pipe over the cryostat, and the smoke went close to the cryostat, hit some unseen barrier, and very fast went up. And it was pretty amazing. He repeated this several times and said, "You are working with magic things." And he left. So that was the beginning.
After months of investigation, Podkletnov concluded that what he created was an anti-gravity field.
So we have a vacuum chamber with a disk which can be rotated over 10,000 rotations per minute. And this is a weight sample which can move freely over the disk. And when the disk reaches a certain speed of rotation, it exerts a repulsive force on the weight sample and pushes it up. In fact, this is a direct demonstration of the gravity fields. This gravity field is, in our case, repulsive. And as you can see, the repulsive force is pretty big.
Hearing about the experiment, Ron Evans organized a team at GreenGlow to try to recreate Podkletnov's breakthrough, but they didn't have the budget to work with a highly specialized superconductor.
We couldn't replicate what he'd done, so we couldn't say yes, he had found an effect, or no, he hadn't.
By now, Mark Millis at NASA also wanted to know if there was something in Podkletnov's claim, and he had a much bigger budget.
We found people who replicated the experiment with Podkletnov's help, and they even had 50 times the detection sensitivity that Podkletnov had had, and did not find any effect.
Despite exhaustive tests, no one seemed able to reproduce Podkletnov's so-called gravity field.
I think Podkletnov had jumped to a conclusion, had seen some things, and did not take the rigor to go through and make sure that he wasn't misleading himself.
Meanwhile, news of Podkletnov's breakthrough had been leaked to the press, and the resulting media storm ultimately forced him to leave his university position. So Podkletnov went back to Moscow to work in secret, and by late 2001, he had claimed he had a new way to manipulate gravity. Wary of the Western media, he contacted the one man he trusted to give him a fair hearing, Ron Evans at GreenGlow. Because of his security concerns, Podkletnov was only prepared to tell Ron the basic concept.
I presented to him my latest works with impulse gravity generator, which gives a very short impulse of gravity waves.
It's really a giant spark plug, really. But according to Dr. Podkletnov, someone way away, a kilometre away, on the balcony of some flats in line with the beam, was still able to detect a slight effect. That was incredible.
For years, the gravity pulse concept remained shrouded in secrecy and stayed unproven. But by the early 2000s, a new generation of scientists had picked up the baton from Project GreenGlow, including Dr. Martin Tajmar, professor of space systems at Dresden University.
If you look for a challenge, always look for a big challenge. The ultimate challenge I can think of as a scientist is to control gravity. That's maybe the most difficult thing there is, right?
Martin is about to comprehensively test Podkletnov's concept once and for all.
His claims are that they can drill holes into brick walls and this kind of stuff, which is an extraordinary claim. And if you have an extraordinary claim, you must have extraordinary proof. Anti-gravity is a kind of synonym for the impossible. But always be ready for the surprise.
This, in effect, is Podkletnov's gravity pulse generator, recreated by Martin and his team. As Ron Evans guessed, it's based on a kind of giant spark plug, essentially 2 electrodes in a box.
Basically, you have 2 electrodes, one here and one here, and you're running a very, very high electric current discharge through that.
This discharge goes through a superconductor. According to Podkletnov, this somehow creates a pulse of gravity, which is picked up by a sensor acting like an electronic pendulum.
And let's say if you have here a pendulum here, that when this gravitational impulse hits the pendulum, you will actually get a deflection of the pendulum. And so the claim is that this is actually also creating not only an electric discharge, but a kind of a gravitational impulse, a push to something at a distance.
The superconductor is cooled with liquid nitrogen to remove its electrical resistance. Podkletnov claimed the resulting massive electrical discharge creates the gravitational pulse. They switch on the power to charge up the system and wait for the discharge.
Counting down.
There is a reading.
So here's the data. Gravity goes with the speed of light, so you should see an instantaneous peak. And then the sound from this bang, this takes some time until it arrives. So we should see 2 distinct peaks because we have such a high time resolution. So that's the acoustic impulse, and exactly here, that's where the gravitational impulse should be, where we don't see it.
The sensor felt the sound wave from the spark, but no gravity pulse.
That's the most sensitive sensor there is in the world. And we don't even see something out of the noise. So how can you make a claim to say that you move things meters away or that you actually push pendulums away? So that's really outrageous claim. We haven't seen something not even remotely like that. So unfortunately, but yeah, so far, no luck.
None of Podkletnov's methods seem to be able to alter gravity in the lab. Could the reason be a simple problem of scale? There is one industry that has to deal with gravity on a planetary scale: the space business. They're always clamoring for some form of gravity-beating propulsion. Mark Millis ran NASA's Breakthrough Propulsion Project. One of its long-term goals was to move away from using rockets. The problem with rockets is not that they can't beat gravity, it's the amount of thrust they need to do it.
If you think about the Apollo spacecraft, and you imagine here's a Saturn V, the very tip of that and then a little bit below that was the actual spacecraft itself, and all the rest of this was the propellant, the rocket fuel, and that's just to the moon.
NASA plans to get humans to Mars and back within the next 15 years, and maybe one day beyond the solar system itself. But just the Martian step seems impractical with conventional rockets because leaving the Earth's gravity takes so much fuel.
The farther or faster that you want to go or more that you want to carry, you need this extra propellant to do that. And then you need extra propellant for the extra propellant, and it adds up exponentially. If you wanted to go to our nearest neighboring star, which is over 4 light years away, and you wanted to do it with the kind of rockets that are on the space shuttle, and say you want to do it in 50 years, you're having to go 1/10 of the speed of light. Well, the amount of propellant you need for that journey is about the mass of our entire sun.
For Mark Millis and NASA, the focus was less on controlling gravity itself than finding ways to get to the stars. They didn't care how long, as long as it didn't need rocket fuel. Then, in 2002, a new device appeared that seemed to offer a solution. Invented by a former defense research engineer, Roger Scheuer.
The big advantage of M-Drive is that it's a device which creates a force, but it doesn't have to shoot out a propellant out of the back.
Instead of using rocket fuel to create thrust, the M-Drive uses microwave energy, just like a domestic oven. Microwaves bounce around inside the box in waves, cooking your food. To stop that energy cooking you, there is a mesh on the door with holes in it.
The diameter of these holes are so small that instead of going through it, microwave radiation is actually bouncing up and down vertically in the hole.
The holes trap the waves, slowing them to a standstill. According to Roger, the narrow end of his M-Drive does exactly the same job.
So the waves are going faster at the large end than they are at the small end. This means that the force at the large end is greater than the force at the small end, which will cause the cavity to move in the opposite direction.
It would only produce a small amount of thrust, but in space, that wouldn't matter.
An M-Drive thruster with continuous electrical power gives you continuous acceleration, and therefore you can achieve very large velocities and travel very large distances.
Roger believes that if he could make it big enough, it could potentially lift us from the Earth.
You suddenly have a lift engine which simply hovers there, or indeed accelerates upwards. So we can obviously envisage launching large payloads into space on an M-Drive driven spaceplane. Essentially, we are no longer looking at ways that we can control gravity itself. We are beating gravity the smart way.
If it works. Though he didn't claim to control gravity, Roger's M-Drive concept was rejected by a lot of theoretical scientists who claimed the basic physics just didn't add up. To settle the argument between the theorists and engineers, Martin Tajmar had the perfect test facility in Dresden. A large vacuum chamber mounted on dampers to isolate it from the surrounding world. A carefully designed rig to hold the drive, with a finely tuned balance to record any thrust. And most importantly, a copy of Roger Scheuer's original M-Drive. Martin's version is small, but if the principle works, there should be measurable thrust. The vacuum chamber is sealed. The thrust recorder inside is so sensitive, it can detect Martin sitting down outside.
We're here in a laboratory on Earth, so there's some seismic movement, so the balance in cells will move just a little bit. That's the noise we're seeing here.
The M-Drive is switched on. Nothing appears to move. But on Martin's screen, there is a reading.
When we turn on the thruster, the balance indeed reacts, and we measure something which looks actually like a thrust. What we measured here in this case is something like 25 micronewtons. That's very, very small. You can compare this, for example, to 1/10 of the weight force of a grain of rice. Incredibly small, still, however, useful, for example. In space, we have thrusters, actually, which have this tiny amount of force, which is still useful to maneuver spacecraft, for instance.
The first results seem positive. But when Martin experimented further, he discovered a problem.
So we had the thruster pointing in that direction, we measured thrust in that direction, and when we tilted it 90 degrees, however, we still measured thrust in this direction, which we shouldn't have. There can still be some major influence from, for example, the power feeding lines that we still need to solve to find out what's the real thrust produced by the M-Drive, if there is any thrust produced.
The great hope of the M-Drive was that as a kind of propellantless rocket, it would at least power vehicles in space, NASA's dream. But NASA didn't pursue the idea any further, or any other gravity-defying concepts, because in 2002, they discontinued Mark Millis's project.
The project ended when the funding for all propulsion research was cut. It wasn't just breakthrough propulsion physics, it was a congressional earmark to build a building in a certain state, and that took all the funding. It happens. Main progress that we made is we took science fiction notions and evolved them to at least the first step of the scientific method. That step by itself is a degree of progress that if I don't accomplish any more, it's like, yeah, that was pretty good.
Ron Evans kept going for another 3 years. But when he retired in 2005, BAE closed down Project Greenglow.
Is it a shame? Yeah, I suppose so. I would like to have worked at a company that actually made this idea work. It was a lovely idea.
When Greenglow ended, the hope of mastering gravity seemed to end with it. If that was ever going to change, we needed to go much deeper into how gravity actually worked. Our understanding of gravity has come down from Galileo, Newton, and Einstein, from observations rooted in the motions of the heavens. Now those same heavens seem to be showing us something that looks remarkably like anti-gravity. The idea that the universe has some inherent form of anti-gravity is tantalizing. If only we could get our hands on it. The problem is, no one knows what this anti-gravity force actually is, only that it seems to originate from space itself.
Although we think of space as this emptiness, the absence of stuff, it actually isn't. There is something that's intrinsic to the nature of space that imparted an energy. And one of the big mysteries is, where does that energy come from?
A number of scientists think the answer to this big question could lie in the very small, the very, very, very small world of subatomic particles. Quantum physics. According to current quantum theory, particles can spontaneously appear from nowhere. Apparently, they just pop into existence in the vacuum of space. Matter and antimatter, which, because they're opposites, cancel each other out in an instant.
The lifetime is 1,000th of 1 billionth of 1 billionth of a second. We are now in an ocean of particle-antiparticle pairs, permanently appearing and disappearing.
Dr. Dragan Hadjukovic thinks something else happens to these particles to produce an anti-gravity effect. For the briefest moment of their existence, these particles can be polarized, like iron filings.
The trouble is to get it in a random orientation. If there is a magnetic field, the random orientation will change. Yes.
According to Dragan, in the same way iron filings respond to a magnet, pairs of quantum particles respond to mass. With matter and antimatter, pairs are briefly orienting themselves in relation to that mass. Matter is attracted to the positive mass of a planet or a star, while antimatter is repelled by it. Dragan believes this creates a halo of anti-gravity dark energy around every mass in the universe.
All these halos together has negative pressure, what is exactly what we need in cosmological equations to produce the accelerated expansion of the universe. It means that there are both positive and negative gravitational charges. So far, we know that gravity is only attraction. it may be that gravity is also repulsion, but not between matter and matter, but between matter and antimatter.
Dragon's theory that the key to anti-gravity lies in antimatter is actually going to be tested. Here in the world's biggest physics lab, at CERN in Switzerland. Not in the famous Large Hadron Collider, but in the improbably named Antimatter Factory, at its Alpha experiment. A team led by Jeffrey Hangst is building a machine that in a couple of years will answer one of the biggest questions in gravity research. Does antimatter fall down or up?
Hi, Dragon.
Hi.
Welcome to Alpha. Come on in. Let's take a look at this machine.
Alpha is part of CERN's ongoing exploration into the nature of matter and gravity.
So right now what we're doing is we're routinely trapping antihydrogen.
But for Dragan Hadžuković, it will be make or break.
Trapping antihydrogen to prepare for the...
If he's right, creating anti-gravity on Earth is at least a theoretical possibility.
From Einstein's perspective, a mass actually distorts the fabric of space and time, or space-time as it's called. That distortion is rather like a well. So here's another object that's moving nearby our mass that has bent space-time, and as it goes past, it bends towards the massive object. But a negative mass would be, in our analogy here, something like a mound instead of a depression, and then you run into problems.
The problem, according to Einstein, is that using a negative mass would mean inverting space-time, effectively turning the fabric of the universe inside out.
And what you end up with is something that's called a runaway problem. You have physics that is just running out of control. It'll accelerate away arbitrarily with zero cost of energy. And if that were really happening anywhere in the universe, we'd see it spectacularly becoming an unstable situation.
If Clifford Johnson and other theoretical physicists are right, anti-gravity propulsion will remain an unworkable dream. It seems the laws of physics simply don't allow it. At least, not as we understand those laws today. Because just as Galileo gave way to Newton, and Newton gave way to Einstein, theories do change. And in the meantime, well, the engineers get on with doing what engineers do, building new kinds of propulsion. Today, that includes NASA. At the Glenn Research Laboratory in Ohio, work is underway to produce new forms of space engines. Ones that really could take us where rockets can't, beyond our solar system.
What we have here is a high-powered ion thruster. And the way it produces thrust, our ions are created inside this ring, and then we establish electrostatic potential that accelerates these ions out and produces large velocities. And what that does is it gives us very efficient production of thrust.
This is an ion thruster under test, pouring out a constant stream of charged particles. It's less powerful than a rocket, but capable of accelerating a spacecraft almost indefinitely.
These systems are ideal for in space. You know, we operate them purely in space because it's very gentle. You know, the thrust level is low, but over time you can develop much higher velocities than you can with chemical rockets.
NASA's focus is on space propulsion, beyond the Earth's gravitation. Yet there is a propulsion concept that aims to revolutionize all of aerospace, resurrected from the days of Project Greenglow. 10 years ago, Project Greenglow ended, and Ron Evans thought official gravity research had ended with it. But today, he's been invited to witness a unique gravitational breakthrough. When Ron first began his gravity research, it started with a question. Could gravity be used to detect aircraft that were invisible to radar? In the 1980s, our complete inability to work with gravity made it impossible. But today, Ron is meeting someone who says he's done it. This time, there are no covert meetings. He's going inside England's Ministry of Defence Research Laboratory at Porton Down.
Ron, good morning. Welcome to the Defence Science and Technology. This is
Neil Stansfield heads a department here that looks at what they call disruptive technology. And they've taken a potential step on the road to gravity control using quantum engineering.
So what we have here is our quantum gravity gradiometer. It's a small system. At the heart of the device, we have a vacuum chamber.
The sensor uses lasers to freeze a cloud of atoms. This cloud responds to disturbances in the Earth's gravitational field caused by a moving mass.
The atoms are sensitive enough to detect the mass of my body at a range of about 1 meter.
So your gravitational field is affecting this device?
Yes.
This is the first time Ron has seen anyone actually using gravity.
To me, this is amazing technology. Getting into the quantum, that's really allowing us to do things that were just unbelievable 30 years ago.
Yes, some people use the phrase, they break the laws of physics. I prefer to say they break the laws of physics as we understand them today. 100 years ago, we didn't understand the quantum physics. The idea of being able to measure changes in gravity, science fiction, could never happen. Today we can.
Yes.
Ron Evans' mission to control gravity began here, in a cold, wet corner of Lancashire, where people go to live their dreams, where no one ever worried about the word impossible. For Ron Evans, gravity control is just something we haven't learned to do. Yet.
I'm sure we will one day. It's just a matter of time.